In this short grab bag video, we're going to take a look at two quick things. We're going to look at the stats window in the game view, and we're also going to look at the static dropdown, the static attribute for GameObjects in the inspector. And we're going to start with the stats window, and there are three sections: audio, graphics, and network. And we're going to look at all the options for each of these to see what's going on. In the audio section, the first thing we see is the level, and the level is an indication of loudness, and it's shown in decibels, dB. And the way that decibels work is they're a power of 10 thing, and they always go negative. So a level of 0 would be the loudest sound that's allowed by your computer. So in other words, a level of 0 would be sort of like your audio is at 1. It's at maximum if your audio were to go from 0 to 1. A level of negative 10 is 1/10 as loud. So this is a factor of 10 thing. A level of negative 20 would be 100th as loud. Negative 30 would be 1000th as loud. So a level of negative 74 is basically negligible. It basically means we have no audio. Next up we have clipping. And clipping happens when your game tries to generate a sound louder than your computer can actually produce. And at that point it will just clip it. It will go as loud as it can go, but it won't go as loud as it's being told to play. And this is just an indicator for that. DSP load refers to digital signal processing, and the way that audio works in Unity is that your audio originally exists as ones and zeros, and we have to turn this into a waveform. We have to turn it into a waveform that can be then used to move your speakers in a wave-like motion. So we load it from the ones and zeros into a buffer. That's the first step, and the buffer is a DSP buffer. So basically the DSP load gives us an indication of how full that buffer is. Next up is the stream load. And with audio, we can either preload the audio into memory, or we can stream it in directly from disk. And because streaming is an I/O operation, there's a maximum amount of audio that can be streamed, and this gives you an indication of how that's filling up. The next section is for graphics. And the first thing that you'll see over to the right is an indication of FPS. Now do be warned that this is not actually the true frames per second of your game. What they're doing is they're calculating how much time graphics is taking on the CPU. In this case, it's taking 1.1 milliseconds. And then they're saying, okay, if that's running at 1.1 milliseconds, that's the equivalent of around 900 frames per second. Now, this is just the graphics processing on the CPU. So this will always be sort of a best case scenario. Usually your actual FPS will be somewhat lower. Because in addition to graphics on the CPU, you're also going to have game logic and physics and other things going on the CPU. And then of course on the GPU side, everything's going to be rendered. And if rendering is taking longer than calculating on the CPU, then you'll be what's called GPU bound. In other words, the length of time things are taking to render on the GPU will be what's slowing you down, because the CPU calculations finish while the GPU calculations are still going. You can be on the other side, you can be CPU bound, and in that case, the CPU calculations are taking longer than the GPU, so the GPU finishes and it has to wait for the CPU to finish until it moves to the next frame, and that's what will be lowering your frame rate. So again, this is just a quick indication of the graphics processing time and a quick indication of what that converts to in FPS. And there are better profiling tools, which we'll get to a little bit later. Next up, we have batches and the amount of draw calls that are saved by batching. So basically what we're being told is in this scene, we are doing 9 draw calls. We are sending 9 batches of information to be rendered. And because we are batching things, and in another video we talk about static and dynamic batching, we actually have fewer draw calls than we would otherwise. If we add these two together, we come up with a number of 15. So 15 draw calls corresponds to our background and then 14 objects in the scene. But because we're batching some of those objects, we only end up with 9, and 6 of them are saved by batching. Next up is an indication of the number of triangles and the number of verts currently visible in the scene. And do keep in mind that this is not the total number in the scene, this is just the number that can be seen by wherever the camera is currently looking. In other words, this is the number inside of the camera's frustum. Next up is an indication about the screen. We have the screen size in pixels, and this will change as we choose, for instance, different aspect ratios and so on and so forth for our game. and then the amount of memory for the screen. Next up is set pass calls, and set pass calls is basically the number of times we have to swap out the shader for everything that we're rendering on the screen. And then we have three things listed. We have shadowcasters, visible skinned meshes, and animations. And these are not counted with our batches and set pass calls. These are broken out separately. And the reason is that these things are not batched. Shadowcasters, basically things that cast shadows, and skinned meshes, which are basically characters and other things with bones, and animations. None of these things can be batched. The only things that can be batched are basic 3D models, basic meshes in your scene, and particle systems. So these things are split out so that you can see if these are having an effect on the rendering time. Since they're not batched, if you have a lot of shadowcasters, if you have a lot of skin meshes, these can very quickly start to eat up your CPU cycles for graphics. The last section covers networking, and this is specifically related to Unity's built-in networking. And Unity's built-in networking, it's sort of something that comes for you that allows you to set up games between people without requiring a backend server. So essentially, players can hook up on a local area network with each other, and they can play a game without connecting to some server somewhere out on the internet. Now, the vast majority of games are not built like that. That tends to be something that more like indie games, non-commercial games, and things are built with that type of networking. But most commercial games are going to have a server somewhere. And they're going to have a server so that you have an authoritative copy of the game. Because if players are just connecting directly to each other, it's very easy to cheat. Because there's no authoritative version of the game somewhere on a server that players don't have access to. Any player could just say, oh yeah, I just fired a bullet and it hit you in the head. And there's no way for any of the other players to really check that. So we're actually going to ignore this networking section because in this course we're not going to be covering the built-in networking. Instead, we're going to be talking about sort of the more traditional networking, which is a server-client model. And that covers the statistics window. And you can turn that on and off at any time while you're playing your game. And even when you're not playing your game, it will show you just some basic statistics for this preview that it's generating while your game is not playing, while your game is essentially paused. The next thing we wanted to talk about in this video is in this top right, it's the static dropdown. And this is essentially where we can apply static attributes to a game object. And I just want to go through and mention what each of these things does, because there are different ways that we can mark things static. And some of these have been mentioned in previous videos, and some haven't, so depending on when you're viewing this, you may have seen some of the things that this relates to, and you may have not. So I'm just going to go through the list, assuming that you aren't aware of what these things are, and explain a little bit about what they do. So first up is lightmap static. And this marks an object static, which means unmoving. All of these are going to mean that the object does not move, so that we can calculate lighting, and we can pre-calculate lighting and shadows and things for the scene. Next up is occluder static, and that actually goes with occludee static. These are sort of linked, and these have to do with pre-baking occlusion culling information. These have to do with occlusion culling. And essentially, objects can block other objects in the scene so that they're not seen by the camera, and there's no reason to render those objects. So we can mark things as an occluder, and that is an object that blocks other things. And we can mark something as an occludee, and that is something that is blocked by other things. And we can actually, with occlusion culling, we can have a mix of static and dynamic. We can have some things that are moving, some things that are static. And we can either pre-bake that this is something that's static that's going to block moving things behind it, or this is something that's static that's going to be blocked by moving things in front of it. Next up, we have batching static, and that has to do with static and dynamic batching. And when we mark things batching static, essentially we are saying that they are static for the purposes of static batching, that they can be combined together into one mesh to save us on draw calls. Next up, we have navigation static and also off-mesh link generation. These two are linked. And what these two things do is they work with nav meshes, and nav meshes are a way in Unity of doing AI navigation. And it's a whole system built around AI characters moving along a pre-baked route. So essentially we calculate all the routes that they can travel within an area, and then we bake that information so we can just reference it at runtime. And the last thing is reflection probe static. And that means that this object will not be moving for the purposes of generating reflection probes. And reflection probes are used with the global illumination system. They're used for producing reflections on objects. And since it's often much too complicated to try and calculate every frame the reflection for every object in the scene, we can bake reflections. If we have a static room, we can bake that room into what's called a reflection probe. And at the top, we have nothing and everything. If we click everything, that marks us as static for all of these things. If we click nothing, it marks us as static for none. So these are just shortcuts, and these are the types of ways in which we can be marked static. And whenever we mark static, we're making a contract with Unity that for the purpose of whatever we're doing in here, the object will not be moving in the scene. And that is, in a nutshell, the stats window and the static dropdown in Unity. Just a real quick recap. We have some information on audio that includes sort of how we're streaming things in memory and how we're loading things in memory. In terms of graphics, this is all about what's visible on the scene. It gives us information about draw calls, it gives us information about complexity, it gives us information about a couple things that are not batched. We have networking information, though we're going to be skipping that in this course. And then we can mark things as static or unmoving for a bunch of different Unity systems.